So in a detail lab, we realize for a large scale topology, there are limited amount of physical system present. So you can use containers, and this tutorial will present the use of containers in a detail lab. We'll create multiple topologies and try to demonstrate what are the various features data container system provides. As you can see here, this is the model of operation. You present the topology, the container allocation system allocates the container on a set of data physical computers, and that's how you will get a large scale topology where you can do multiple kind of experiments. Just to give you a brief overview, there are various types of containers where detail lab provide physical machine, which we already saw in tutorial 1, which will be like one node on one physical machine. A QEMU virtual machine will have tens of container on a physical machine. An OpenVZ container will have hundreds, and VueOS process will have thousands. All of these containers provide different sort of functionality, and you can select what exactly you want. So first we'll be creating a star topology, something like this, using a container. And to set it up, we have to use this containerized.py script, which is present in detail lab. Once you SSH into your user's account, you specify a TCL file or a NS file similar to what you provided in a physical experiment what we did in tutorial 1. It's similar, it's just that there will be lot many nodes because we'll be creating a containerized environment with one number of nodes in it. So as you can see, I invoke the containerized.py script, specify the ns file cexample1.ns, specify the group ID, which in our case is EE542, and specify the name of the experiment. It created an experiment in detail lab called cexample1, and as you can see, this experiment cexample1 is created in detail lab. You have to click swap experiment in confirm. So now as you can see, after waiting a couple of minutes, the containerized experiment is set up. You can also see the experiment from here. It's called cexample1. If you see the visualization, it says only one node is present, although in the topology we created a star profile with 9 nodes in it. As you can see, only one node, which is the physical node. The NS file is also very different from what we actually gave to the system. So I will show you what exactly happens. So this is the physical node on which the containerized experiment is created, which actually has the 9 nodes present. So what we did now is SSH into the physical node. If you can see this particular line which I had copied before, this is the physical node on which the containerized experiment is present. Once I SSH'd into this particular system, I went to a directory which is project, the group ID, experiment, the experiment name, and containers. Under this containers directory, you have this visualization.png, which actually lists the present topology correctly, not just the one node which we saw in the detail lab, which was present. cexample1.ns gives you the ns file which you have used. So I've copied this visualization.png into my system, and if you can see, it comes in something like that. So there are 9 nodes, 8 nodes connected to the center. You can SSH into the containerized node. As you can see, I have entered here C0, the name of the experiment, and the group ID, and the data URL. And after USSH, you can do regular command, as in like ping to other nodes. So I'll be pinging to the center node, and as you can see, you can find out the statistics regarding the network. Here I am pinging to the first node from the N0 node and trying to find out the network statistics. So similar to the physical node where you can specify what script you need to run when the nodes start, you can do similar thing in a containerized experiment. But unlike the physical nodes experiment, the containerized node gives relatively lesser options. Also, you basically need to specify the command using the start command feature. The logs from the commands are copied to the start command.out and this particular directory, and the error messages. It's important to note that redirection commands will fail, and it's important that you avoid that. If you really are waiting for logs, these redirection commands won't work. It's better to use this monitoring of these two files to find out how your script is proceeding. Also, because in the Linux string you can only specify certain number of characters, it's a good idea if your start commands do fairly complicated work, you just encode them or like encapsulate everything in a small shell script. That will make things much easier. You can use the ditter web URL to swap the experiment out, or just use the swap exp command on the shell to ensure the resources are removed. Like I mentioned in the start, there are different type of containers you can use. So we'll be now using creating a different topology using different number of different types of nodes. We'll be first creating a queue node experiment which has all QEMU nodes in it, and then we will create a experiment which has mixed nodes. So we created an experiment with 7 QEMU nodes in it. To specify all the nodes are QEMU type, you use ---- default container and specify the type of node you want, which as I showed is the physical node, the QEMU node, the OpenVZ, and open process. Here you specify this command to make it all QEMU, so all the 8 nodes in that same start topology will be of QEMU type. You can also modify the NS file so that you can set some nodes as QEMU and some nodes as of any different type. After the experiment is set up, you use the same thing. Go to the URL in the data lab and swap in the experiment. This will set up the experiment. Once the experiment is successfully swapped in, you can do similar things what we showed for default open VZ node. It's important to note QEMU nodes are a bare bones PC and they allow limited functionality. But what you can do on a QEMU node is set it up so that multiple users directory is logged in. To do that, you need to specify while you are creating the script, you are creating the experiment using containerized.py. You specify ---- prefer QEMU users and the names of different user directories you want to mount it up. Now we'll be creating a mixed node topology, and this will have an open VZ node, and all other rest of the nodes are QEMU nodes. Sorry, I was wrong there. We'll be creating an experiment where all the nodes apart from the center node is of a containerized type. So the center node is a physical node. The rest of the nodes are QEMU nodes and embedded P node. So to create this topology, you call it with the arguments so as you can see here, we ran this experiment see example 4.ns, which is a mixed node profile topology, which has the center node is a physical node. The rest of the nodes, the satellite nodes, are of the various containerized type. Most of them are emu except one which is an embedded p node. You can see the ns file right here. So as you can see, the satellite nodes are QMO node except N9, which is physical. And if you see I ran the experiment, I swapped it in as well. And if you see the visualization, it says 3 nodes are present. This is the physical node, the container. There are 2 container nodes, although the QMO nodes are not being shown here. So there's only one container which contains all the QMO nodes as per this visualization. But the topology remains the same, the star topology which we saw earlier. Apart from that, you can, in the containerized experiment as well, you can set up the various OS which you want. You need to just specify the distribution type. Basically write the template name using this open hyphen open vc and template, and you give this argument for the node to be set up with one of these OS images. So it's similar to what we did in the first experiment, where we set up all the nodes and give it a different OS flavor. You can, similar to that itself. We went through this already, and we also consider the various parameters in the QMO nodes and the users which can be mounted on the user home directory. The packing factor is one of the important things right now. When we saw the experiment, you saw only one. In the first experiment, you saw only one physical node contained all the 9 nodes in the topology, all the 9 QMO nodes. But what that's because the packing factor is set as default. But if you modify the packing factor, which we can see, which we can do using this command, you'll observe that with a packing factor of 2, the 9 nodes are distributed instead of being in one physical machine. So using packing factor, you can set up a different sort of a topology where you can do different type of experiment. I will demonstrate that shortly. So I ran the C example 1.ns, which was basically a star topology with 1 node in the center and 8 nodes on the outside, so total of 9 nodes. But instead of specifying no packing factor, which would set all the containerized node in one physical machine, I specified a packing factor of 2, and that distributed all the 9 nodes in 5 different machines, which you can see here as per this visualization. So far we will be talking about topologies which have less than 20 nodes in it, but now we create a topology with more than 60 nodes in it. So the way we use the topology is using this particular file. So as you can see, It's like there are two centers, so to speak, and 20 nodes for like three collectives, so total of 60 nodes. It is supposed to look something like this. There is one center and three localized center, each with 20 nodes in it. So basically three subgroups. uh, Now you can modify the topology so that these containerized nodes come on one PC or different multiple PCs. And the way you can do that is using the pass 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 pack factor. So that is like multiple passes and packing different containers in different physical nodes. If you see the SSH command I run here, it says it's a comma separated list, which is 0:1, 1:20, 2:10, 3:5. What this signifies is for 0th pass only one physical node. For first pass, the packing factor should not be more than 20. 2 has 10 and the third has 5, and that groups everything up. And you can see the modified uh, passing, like how they get grouped using this particular script, which creates which actually represents based upon each physical node. So I mean, I'll copy this example 7.png which was generated by this script back into my hard drive, and then we'll see how exactly that looks. So as you can see, I transferred it back into my hard drive and I opened the example 7.png which was created, and it looks something like this. So as per the criteria which are specified in pass 0, only one physical node. On the second pass, 20 can be accommodated, so all 20 are there. In the second pass, you say it was 10, so they are split in three separate groups. This is the second pass. They are split in three separate groups, and once we specify such passes using comma separated, you can see there is a sort of an asymmetry created. And the way it works is as described in the tutorial. We use a separate software called Metis graph partitioning software, and it it takes into account the packing factor and how is the intercommunication cost between these two nodes. So if you really want it symmetric, what you can do is either create your topology using a different packing factor, or what you can do is specify some different switch called hyphen hyphen node only option. What this does is it consider these arc costs as 0, and then the distribution is symmetric across the groups. So depends upon you which kind of experiment you want to run, and you can create either of these two emulated networks.